In Lesson 9.2, Plane Curves and Parametric Equations, we will begin our rather short exploration of parametric functions. That is, functions in which each coordinate, the x and y coordinate, are uniquely and distinctly defined respective to the value of a third variable, which we call the parameter. Now, at this level of mathematics, that parameter often takes the form of t, representing time. In other words, the x and y coordinates are both themselves a function of time. But we will see a couple examples where the parameter is theta, meaning that the x and y coordinates are taken respective to the angle that's being measured at that point, or we could use any other parameter. Now, this is only a basic exploration. In further math courses, you'll get to study parametric surfaces, which of course are where x, y, and z, all three are uniquely and distinctly defined by a third parameter, or rather a fourth parameter. And we can study all kinds of parametric structures. The double helix probably being the most common example of a three-dimensional parametric function. Anyway, I'll leave those for you to explore. We're just going to just scratch the surface, to be quite honest. In this lesson, we'll be filling in tables like you did in Algebra 1. We'll be plotting points like you did in Algebra 1. The only difference here is that we need to understand that with parametric equations, the order that the points occur is important. If time is your parameter, then our function will show us where a particle or where a location is at a given time. So the order that we plot the points is important, and you'll see examples of that as we go on. Also, we'll learn in this lesson how to take two parametric equations representing x and y and transform those into a singular rectangular function. And those are the functions that we're used to dealing with. So there's really not too many notes to look at in this lesson here. Rather, let's just jump straight into example A. So for all three of our examples in this chapter, and for most of your assignment problems you'll see, really all we need to do is make a table of values. We'll be given the value of the parameter, which in this case is t. This is probably a function of time. Anyway, we'll be given different time, and for each one of those, we're going to find the x and y coordinate of the parametric function. After that, we're going to graph our parametric function, and then we're going to write the corresponding rectangular equation represented by the parametric function. So just to be clear, parametric functions are functions of a parameter t, in this case t, but x and y are actually two separate equations. So what this could mean is that the x-coordinate could be going at one speed, the y-coordinate could be going at another speed altogether and could reverse direction. They could do all kinds of crazy things. But the easiest way to attack these is simply fill in the table of values. So I'm not going to spend a whole lot of time with this. Here is our x equation, and I'm just going to run through and fill these out. So we're going to start with 9. When the time parameter is -2, that will rise us up to, or actually lower us down to 7. And in fact, I'm going to go down by 2 every time one value of t passes. So if I just fill this out as such, there is our x-coordinate over time. Now, we can't plot the x-coordinate. We need a y-coordinate to match up with it. And so our y-coordinates are going to look like this. It's actually going to start at -7, and we'll go up by 3 for each time interval. So let me just go ahead and fill this in, and hopefully you didn't have too much difficulty simply filling in a table of values. Now, where we're going to go from here is we need to graph the curve represented by this table, and it does indicate to us to be careful about the orientation of the curve. In other words, don't just plot these points and say, boom, there it is, I'm done. It is important that we put arrows to signify which direction or orientation this graph is going. So, at time is -3, I'm going to have a point, a rectangular point at 9, -7. This is where I'm going to start. From here, as time goes up, time is going from -3 to -2, my x and y values are going to change, and I'm going to find myself at 7, negative 4. So I see that I'm starting here and going in this direction. Let's see if that continues. I'll next end up at 5, negative 1, 3, 2. Oh, certainly. You can tell that I am going up and to the left as time goes on. And so there is my parametric graph. I'm not very good at drawing straight, but this doesn't look half bad. All right. Now, how do I signify orientation? If you just look at this graph as it is right now, it just looks like a line. Just looks like a line. Time isn't involved. It just goes. But to be careful, to show the orientation, we generally just put a few arrows along the line to show that we actually are going up and to the left. And you can see that as time goes on, certainly my x value is decreasing, my y value is increasing, and both of those jive quite well with what you see here. So the last thing I need to do now is I want to write the corresponding rectangular equation by eliminating the parameter. Now that might sound a little confusing, but what they mean by eliminate the parameter is first, let me write x and y in terms of the parameter. Well, that's actually already done for us. We're given that x equals 3 minus 2t, and we're given that y equals 2 plus 3t. So x and y are already written in terms of the parameter. Let me go ahead and switch that around. Let me write the parameter in terms of x and y. And what I mean by that, for the x equation, if I subtract 3 and then divide by negative 2 and all this good stuff, what I'm going to find out is that x minus 3 over negative 2 is what the time parameter equals, time in terms of x. Well, let me do the same thing over here with my y equation. If I do, I will end up with time equals, let's see here, this will be y minus 2 over 3. Now, why did I do that? What's the point? Well, the important thing to notice here is that both of these equations are equal to time. And so what I can essentially do is just get rid of the times and say this equation equals this equation. There's a property in geometry that you might be familiar with that was similar to this, where if one equals this and this equals this, then that equals that. It's the same idea here. So if I write this as x minus 3 over negative 2 equals y minus 2 over 3, you can cross multiply. You can multiply by 6 to get rid of the denominators. You can go about this however you like. What we should end up with, either way, however you do it, is 3x minus 9 equals negative 2y plus 4. And if I want to write that as a rectangular equation, I'm going to write this in terms of y. We can call this a slope-intercept form if you so choose. But what we're going to end up with is y equals negative 3 halves x plus 13 halves. A little bit of algebra will get you that answer. And I don't really need to prove to you that that is correct. I'm sure you can do that. Now, did we lose anything by turning this into a rectangular equation? This equation, if you look carefully, is the same equation as this line, but we have lost a very, very important aspect of our parametric function, and that is we've lost our orientation. When we got rid of the parameter, we lost the orientation. So the graph still stands, right? The graph is what it is, but be careful. If you do this rectangular equation, we're not going to have any clue on which orientation the graph goes. So be very careful. I will tell you, not all parametric functions will graph as lines. This was a very simple example, but let's take a look at example B and see a parametric function that is not a line. In our second example, the first thing I want you to notice is an anomaly with the parametric equations defining x and y. Take a look at them real quick. The y equation looks perfectly fine, no big deal. Whatever the parameter is, I'm going to subtract 1. That's my y value. But take a look at the x value. Something really strange is going on here. Can x ever equal 1? Is there any value of t that I can use so that x equals 1? Certainly, time could equal 0. There's nothing to prevent time from being 0. But when time is 0, what happens to the x-coordinate? And these are all questions that will be answered as we go through, make our table of values, graph it. In our rectangular form equation, when we see that, we'll answer a lot of those questions more to our familiarity with how we usually deal with equations. So let's just go ahead and begin by filling in this table. When t is -3, you can see that x is going to be 1 minus a third. So I will simply write 2/3 in here for x. When time is -2, we have 1 minus a half. And when t is -1, we have 1 minus -1. Or 1 plus -1, rather. So that's going to be 0. Now, here comes our interesting situation. When t equals 0, what's going to happen to our x value? Well, it's going to be undefined. We cannot have a 0 in the denominator. So we simply say there is no value of x when time equals 0. But moving on, when time is 1, we have that. When time is 2, we'll jump up to 3/2. And when t is 3, we will have 4/3. So hopefully none of that is outside the bounds of reason. Our y is going to be very simple. Whatever t is, we just subtract 1. So I should be able to run through this. Let's see here. And it's going to look like this. Nothing special. So let's go ahead and graph all these points. Remember, we need to be careful about the orientation. So I'm not going to graph them randomly and haphazardly, but rather I'm going to start at the earliest time and move on to the latest time. So let's see how this looks. 2/3, -4 is going to be a point about right here, let's say. From there, we're going to go to 1/2, -3, and then we're at 0, 2. And then we have this undefined thing, so I'm not really sure how to graph that. But what I do know is that we do have something going like this, and it is going in this direction. All right, well, let me take a break from that one. At t equals 0, I can't graph that. When y equals -1, x apparently is undefined. And actually, that does tell me something. Check this out. When y is -1, x is undefined. So what that means is I'm actually going to have an asymptote here. Again, this is where y is -1, x is undefined. So that's pretty interesting. This makes me wonder if this is going to become asymptotic to that y equals -1. I asked that question now, but I think it's going to be answered here in just a moment. Let me continue on with my table of values. I'm going to pick up right here, and that's going to be at 2, 0. Then I'll move to 3/2, 1, and finally 4/3, 2. So this is also doing something kind of interesting. And I have a feeling that this is actually just going to grow and grow and grow, and will never hit x equals 1. It will never hit x equals 1. Well, why is that? Let me go back to my original question. For what value of t will x equal 1? Look at the x equation. Is there any value of t for which x equals 1? Hopefully you can look at that and say, no, that's not possible. So I am actually going to draw another asymptote where x equals 1. We'll never be able to reach that, or therefore cross it. So now I kind of have an answer as to this. This probably will keep going like this. And this will actually come from here. All right, so this is a very, very interesting graph here. I'm actually starting with this branch, and it's going to the left forever and ever and ever. Then it's actually going to pick up over here all the way to the right and move this way. So this is my first time part, and this will be my second time part of what appears to be a hyperbola of some sorts. So let's go ahead and find the rectangular equation and see if this leads to anything that looks familiar, like I feel it will. Again, there is my x equation, and here is my y equation. So let's solve both of those equations for t. Over here, what I will get, and again, I'm going to skip a few steps, but if my math is correct, I should get that time equals 1 over x minus 1. And over here in my y equation, time is simply going to be y plus 1. So at this stage, I can go ahead and eliminate my parameter and say these two equations are equal to each other. Let me go a little bit further with this. If I multiply by x minus 1 to both sides of this equation, I get something that looks like that. And then if I do want to turn this into a function y that's of x, you can do the math here yourself. But I'm going to get an equation that says y equals 1 over x minus 1 minus 1. Now, that is my final rectangular equation. And if you look at this, it makes a lot of sense. What happens when x equals 1? What happens when x equals 1? We have a vertical asymptote. And you can see that for yourself right here at x equals 1. We could tell that with the parametric equations. Furthermore, if you're familiar with the parent graph of this, in other words, if you're familiar with the graph of y equals 1 over x, this is simply a transformation that is 1 to the right and 1 down. So 1 to the right causes my vertical asymptote, and 1 down causes this horizontal asymptote. So I was correct with both of my asymptotes, even though I looked at them in the parametric sense. So that's how all this is done. You fill out a table of values, you graph the points in a time-wise manner, and then you solve both equations for t, set them equal, and solve. You get your rectangular equation. Our third example is going to be a little bit different, a little bit more complex. Our new parameter is going to be theta, so we're not going to be looking at time any longer. We're going to be looking at angles now. That will affect a few things, but so long as you're good with your trigonometry, we should have no problem with our third example. And here is our third example. Again, we do have a couple trigonometric functions. So filling in the table will require a little bit of pre-calculus knowledge. For the sake of time, I'm just going to go ahead and fill this table in. What I recommend is for you to pause this video and take just a second to fill it in yourself to make sure that you are up to date with your unit circle and all that good stuff. However, here are the values. For the x-coordinate, at least, they're going to look like that. They are cyclical in nature, of course, this being a trigonometric function. And our y-coordinate will carry these values as theta increases from negative pi to positive 2 pi. Now remember, our parameter this time around, I should mention, is not t as it has been for the last two examples, but rather theta. So that's saying that our x and y coordinates are not a function of time, but rather a function of the angle through which we're passing. You can kind of consider these to be angles on the unit circle if you want, if that helps. So here are going to be our x and y coordinates. Let's go ahead and plot these in a time-wise fashion. Even though our parameter is not time, we still have to go in a specific order so that we keep the orientation. We'll start at 2, negative 1. As indicated when theta is negative pi, and we'll move up, 4, negative 3. We'll go here, then we'll have 6, negative 1, 4, 1, 2, negative 1, 4, negative 3, and it looks to me like we're going to be going in a circle. Now, of course, if we plotted more points, we could see that this actually is a circle and not some weird funky diamond like you might try doing if you just connect them with straight lines. But this would be a circle. Interestingly, it is a circle going in the same orientation as our unit circle. It's not a unit circle necessarily because there are 2's in front of these sines and cosines here. But this tells me that it is going to be a 2-unit circle, if you will. Of course, it is not centered at the origin either. You'll notice that the constants in the x and y do kind of give me my center, and then these give me the radius of the circle. Now, all that information could be very useful when you're trying to come up with the rectangular equation for this graph. My hope is that you can just look at this graph, realize it's a circle, and just give the equation. But let's say you were not able to, or furthermore, let's say this was an ellipse or something along those lines. If that was the case, let me go ahead and write out our x and y equations and see how in the world can we solve for theta in these equations, because that's what we're going to have to do. if we're going to eliminate the parameter, that means we need to solve for theta. Well, that looks like it's going to be a mess here. In fact, I would argue that theta over here is going to be the arc cosine, or the inverse cosine, of x minus 4 over 2. That is not pretty. And the theta over here for our y-coordinate is also going to be not pretty. It's going to be the inverse sine of y plus 1 over 2. These are hideous. These are hideous. Am I going to set these thetas equal to each other and then solve for arc cosine and arc sine? I personally don't feel like going through all that. I think that could be quite a pain. And so what I'm going to do is consider a right triangle. And this is not to scale, it's just a whatever, standard right triangle. If I call this angle right here theta, then I can take a look at this function. Theta is the arc cosine of x minus 4 over 2. And if I'm talking an arc cosine, you should be able to place the x minus 4 on the adjacent side and 2 in the hypotenuse. Notice also that theta is the arc sine of y plus 1 over 2. So I should be able to place those as well. Y plus 1 will go on the opposite side from theta, and 2, again, is our hypotenuse, so that's pretty handy. Now, I have this random right triangle with its sides and hypotenuse labeled. What do I do with this? Well, whenever you have a right triangle, the first thing that pops in your head should be exactly what we're going to use here, and that is the Pythagorean theorem. So, let's see what this looks like. I have a squared plus b squared equals c squared. And in fact, that is the equation that represents the circle that's given right here. This is the rectangular equation. Notice where the center is. It's at 4, -1. Sure enough, 4, -1. Notice what the radius of this circle is. It's 2. And sure enough, the radius here is 2. So, it's a much different problem from the first two examples. A little bit of trigonometry thrown in there will usually result in some kind of conic section or another. So luckily, we've already learned about conics, just recently, in fact. But really, at its base, parametric equations are no big deal. Come up with a table of values. Plot each point in sequential order. And then when you draw it, you should have a graph of the parametric function with the orientation intact. With that being given, we can go ahead and find the rectangular equation for our graph. We'll lose the orientation, but we still have all the pertinent features otherwise. So hopefully, although this is quite a bit of information, hopefully it will be enough to get you through the 9.2 assignment. And so on that, I will wish you good luck.